And before we introduce today's speaker, just a couple of announcements about some upcoming events. The next Nano at Tech will be on April 9th, and I believe, yeah, it's here in this room in Marcus. And the speaker will be Professor Shiming Yu from Electrical and Computer Engineering. The day before that, on Monday, April 8th, the graduates in nanotechnology group will have a guest speaker, Professor Yi Kui from Stanford University. And there are flyers in the hallway about that, and I think in the back of the room there's a little, also the same flyer, so you can see that. So it's a pleasure to invite today's, or to introduce today's speaker, Professor Jayakanth Ravichandran. He got his bachelor's and master's degrees in metallurgical and materials engineering at Indian Institute of Technology before getting a PhD in applied science and technology at UC Berkeley, and then doing postdoctoral work at Columbia and Harvard before starting in 2015 as an assistant professor in the Department of Chemical Engineering and Materials Science, as well as electrical and computer engineering at the University of Southern California. He's won a number of awards, most recently being named an early career scholar by the Journal of Materials Research. And I'm going to turn the microphone over to him.
Thank you for the nice introduction, and it's a pleasure to be here, and thanks a lot for the invitation and to visit to present some of the work that my group has been working on for the past 4 or 5 years or so. So as the title of the talk suggests, this talk is going to focus on the particular class of materials called as Perovskite Chalcogenides, and specifically the theme of the talk will be on dimensional control of light matter interaction in these materials. Okay, so before we go into the details of these materials and how they behave, I want to give a very broad perspective of why we care about these materials and what is the background for this. So the starting point for these systems is the idea of we living in the semiconductor age. Semiconductors have powered literally many of these high performance devices that we hold in our hands every day, right from your phones to laptops and various lighting devices, the TVs and LEDs that you see. So I have given a few different cases here. So I show the transistors, which are part of all the computers, and also the smartphones that you see, solar cells that are increasingly powering our homes by converting sun's light into electrical energy, various types of lasers that are used, including the laser pointer that you see. Some of these pointers have semiconductors in there, and the LEDs, specifically the blue LED, which was a big breakthrough that won the Nobel Prize in 2014. So the research on semiconductors has always remained interesting enough to throw up some new surprises, and that has given rise to Nobel Prizes right from 1956, when Shockley, Bardeen, and Brattain won the Nobel Prize for transistors. And then the latest one, as I mentioned, was for Akasaki, Amano, and Nakamura for their inventions on gallium nitride for lighting applications. So in between these two Nobel Prizes, which were primarily given for a lot more applied areas that we see every day, there were quite a few Nobel Prizes given for quantum Hall effect and fractional quantum Hall effect. So these are interesting physical phenomena that seem to happen in very high quality semiconductor 2D electron gases. So overall, there is a lot of scope for doing technology-based impact and also basic science work in semiconductors. So that seems to keep powering our research even today. Okay, so what is the current status now? So as many of the people in electrical engineering here and everywhere has been forecasting, and also we are at the end of the Moore's law right now. So Moore's law is something that has predicted that the number of transistors that we have in our computer chips has continuously increased to twice as much as number every 18 months or so. And this scaling has been very successful despite the impending end of the scaling that has been predicted for years. And we are at a point where we have really reached that end, and the scaling has slowed down, and even the semiconductor reports, roadmap studies that used to be predicting the next stage has stopped now. So with the impending end of Moore's law, how can we continue to improve the computational systems that we use every day, which are primarily powered by semiconductors? Okay, so that's one part of the question. And just to make a small joke about the situation, in the 1990s, we had a really bare bones computer with scale transistors, and that was not fast enough to run our Mario games or so on and so forth. But in 2015 or so, the computers became much more powerful, but still was not fast enough for what we do. But in 2035, we are really optimistic about, despite the Moore's law's end, I'm pretty sure we'll figure out a way to get very high performance computers and still complain that it is too slow. Maybe it is several orders of magnitude faster than this. There are some clues as to what sort of computing paradigms that could get us there, perhaps. So I'm going to make some areas where continuing to work on new or improving existing semiconductors can still make an impact. Taking the computing as a starting point, there's interest in developing beyond Boolean logic or von Neumann computing architecture that is there in all of computers, going into neuromorphic computing to analyze things that are not very easily done by conventional Boolean logic, and also quantum computing as a means to do high performance computing in a very efficient, fast manner. So these are areas where developing new materials, maybe even semiconductors, could play an important role. Energy is another area where semiconductors continue to play an important role. Many of the solid state energy conversion systems still require better and more powerful or high performance semiconductors. And last but not the least, a lot of our communication and sensing applications also require better semiconductors. One of the important issues that increasingly is becoming relevant for things like autonomous cars, for example, is the ability to see through what is beyond the human perception, which is in the longer wavelength regime of infrared. And there are many areas where there is atmospheric transparency windows in the infrared, but we don't have the right sort of devices and technologies or materials to work through that. So there are lots of applications that are emerging. So in all these cases, it is extremely important for us to continue to invent new materials, new semiconductors that can fit in all these functionalities. So with that, as a backdrop, so let's think about, let's try to put all the materials or semiconductors that we have worked with are known for years in perspective to see what we can learn about it. So a couple of quantities that define semiconductors. One is carrier mobility. The mobility is a measure of how well your carriers transport in materials. And the other aspect is carrier density. Is it how many carriers that you can pack in a given volume of material? So these two quantities tend to go in opposing directions, so they are contradictory to each other. So as you can see, some of the high mobility materials like graphene or 3,5 materials tend to have extremely low carrier density because the band structure itself is built such a way that they are very highly dispersive and they can only hold a small amount of charge, but they can transport extremely efficiently. But as you move down to the periodic table, move down to other materials, what you'll notice is that the carrier density can gradually increase, but that comes at an expense of carrier mobility. So we always have this issue of low carrier mobility, high carrier density, or high carrier mobility and low carrier density. So how can you get around this, and will getting us somewhere here open up new opportunities? And that's the big overall question that we want to ask. So to give a context to this, if you look at these materials, there are certain things that will jump out right away. Many of the materials that are shown within the high carrier mobility regime tend to have conduction and valence bands that have s and p orbital character. And having this orbital nature is the basic essence that decides why your carrier densities are low and the mobilities are high, because these bands are very, very dispersive in nature. But as you move down, as you get to transition metal-based systems, you move to the d-band conduction, where the carrier density goes up, but at the expense of the carrier mobility. But most of the d-band systems that people have studied in the past has been complex oxides. But recently, there's more interest in transition metal dichalcogenides due to the interest in two-dimensional materials. But these materials, the question is, can we take these systems, retain this carrier density, and somehow try to push up the carrier mobility? So that needs some understanding of what are all the different factors that affect carrier mobility. One is, of course, your large density of states inherently limits the mobility. The other aspect that also limits the mobility is the detailed scattering processes that happen in your system. Can you control those? And that will be the key answer to this puzzle. So one way to think about this is, so let's take this case of strontium titanate, which is a very nice semiconductor material with d-band conduction. And if you take this system and somehow maintain the framework that is present here, and look at how the interaction between the d-band conduction that arises from the b site element and the anions is that these two elements tend to have very large electronegativity difference, and hence the interaction between these give rise to strong scattering of electrons in your system. So now, if we can somehow retain this structure and reduce this electronegativity difference between these two elements, you have a mechanism towards increasing the mobility of your system. So one way to do this is by taking this system, looking at oxygen has very high electronegativity, and moving down the periodic table, you go to sulfur and selenium, the electronegativity drops. So now this is a mechanism by which you can go for a material that has sulfur and selenium instead of oxygen in this framework, where you can have much lower electronegativity difference and hence much better carrier mobility in your system. So that's our general prediction, and it also holds true because transition metal dichalcogenides do have much higher mobility than oxides. Okay, so our question was, can we find some material with this slightly better carrier mobility with high carrier density? And we think transition metal perovskite chalcogenides is a candidate system. Okay, so now let's before I go into talking about these materials, first thing is I need to define what is a perovskite, and also give some context on why we arrived at this material system. Okay, so the first step is to define what is a perovskite. So perovskite is a very nice ternary material system which has a ABX3 formula that's shown here, where the B element typically is something that sits on the center of your unit cell, and your A element sits on the corner of the unit cell, and your X is something that sits on the faces. Okay, typically the band structure of this system, if we were to talk about a scenario where we are taking this early transition metal elements that are shown here, then your conduction band is made of the orbital nature of the B site element, and your valence band is made of the orbital nature of the X site element. Now, one of the interesting things that will jump out if you look at this periodic table is that the candidates for this A, B, X elements are all over the periodic table. So essentially, you can pick most of the elements from the periodic table, and you can build a material that has the same chemical formula of ABX3 and will either fall directly as a perovskite or something that is related to it. So that's what makes perovskite materials an interesting candidate to study, because you have so much structural and physical chemical variety that you can build a whole slew of compounds to study and see if they can be applied for various applications. So now, just to give a context, I'm going to start off with the well-known perovskite oxides and give some examples to motivate why perovskite chalcogenides could be of interest. So as I mentioned, the d-band conduction gives rise to large density of states. One way to manifest large density of states is by comparing a complex oxide, lanthanum cobalt oxide, against crystalline silicon. Silicon is a sp bonded material. It has a relatively low density of states, and one way to compare density of states between materials is to just measure absorption coefficient of these materials. As you can see here, crystalline silicon has very low absorption coefficient because it's an indirect band gap material, but even amorphous silicon tends to have very low absorption coefficient. But if you go to the lanthanum cobalt oxide, which has the D band conduction, the absorption coefficient is a factor of 2 or even almost half an order of magnitude higher. That tells you that the D band conduction can give rise to a large absorption coefficient. So this is interesting for solar cells, for example. If you can make a D band system and still have some reasonable mobility, then you can think of ultra thin absorbers, and they can also give rise to good carrier separation mechanisms. Now, let's talk about few more cases. This is especially interesting if you are interested in the angular momentum of the carriers that are present in your system. So one of the interesting things about D-band systems is that it has various different orbitals that have very different angular momentum. Okay, so that means if you can build materials that can put carriers in various different orbitals, you can assign various different angular momentum to these electrons. So you can take advantage of the angular momentum differences that are present for carriers in various orbitals. And recently, people have shown that in the case of transition metal dichalcogenides like MOS2, you can do valetronics. In this specific case, it is not due to the orbital nature, but it is primarily due to the differences in the two sides, equivalent sides that are present there, which gives rise to very different K points, and hence you get orbital angular momentum selective excitation of carriers. So this is especially of interest for people who are interested in quantum applications broadly defined. Okay, so last but not the least, I'm pretty sure people would have heard perovskites in a completely different context, which is the halides. And halides have really taken the solar cell community by storm. They came in almost 10, 15 years ago, and within a short span of a decade or so, they have quickly risen up and have achieved 20 to 23% power conversion efficiency, which is even better than some of the long-standing candidates such as CATL and SIGs and so on and so forth. So in a broader sense, perovskites can provide you a much larger structural and chemical tunability, which is not necessarily present in various other transition metal compounds. And also, you can get this chance to achieve high mobility and high carrier density, which is what we are trying to explore in this talk. This specific talk, even though we won't get to that high mobility, high carrier density part, but we'll talk about the general features of these materials first, because there is very little known about these materials. So I'm going to start off with the same perovskite structure and try to focus on a narrow set of compounds for this specific talk. So the ones that we are interested in are early transition metal based systems, which means your B side has titanium, zirconium, and hafnium, and your A side has calcium, barium, and strontium, and your X side is sulfur and selenium. Okay, so it turns out these materials can assume one of the few different types of crystal structures that are shown here. That allows you to have the octahedral connectivity show very specific dimensionality, and that's what we're going to leverage in this specific talk and show that light can interact very differently when your octahedral connectivity is very, very different. Okay, and that gives rise to various different interesting applications. So the true perovskite is defined by corner sharing of these octahedra forming a three-dimensional network. But once you have ionic sizes that do not let your system crystallize in this 3D network, you start getting this edge sharing network, which is a quasi 1D type system, which has a lot more network connectivity than a true 1D connectivity. Then you also have this hexagonal variants where you have phase shared connectivity between the octahedra that gives rise to 1D chain-like behavior. So you can go from 3-dimensional all the way to 1-dimensional by just changing different elements that are present in your ABX3. Last but not the least, there are also natural superlattice structures which form 2-dimensional layered variants of this 3-dimensional compound by just inserting an extra AX layer in between this ABX3 blocks that are present. So you can basically take a system, make it go to 2 dimension and also 1 dimension, and in all these cases you should be able to see completely interesting different physical phenomena, and that's what we're going to go over one by one in this talk. Okay, so let's look at this particular graph that I've shown. So this is a prediction of the band gap for these various compounds, assuming it crystallizes in one of these 3 phases. In principle, only one of them is going to be the thermodynamic phase, the ground state of the system, and it's possible that you may have another phase stabilizing close to room temperature. But this is a good starting point that Shengbai Zhang group at RPA predicted for us to start taking some of these compositions and try to look at it. So the first thing that we started looking at is this strontium zirconium sulfur 3 and barium zirconium sulfur 3, because you can see that the band gap seem to match nicely with the solar optimal value, which means there is a chance of looking at single junction solar cells based on these materials. So when we started working on these systems, we knew heuristically this made sense to look at, but we didn't know whether anyone has ever made it or not. But turns out people have been working on this. There are chemists who have synthesized everything that you can ever think of, and they would have just structurally characterized it and thrown it in dustbin. So in the 1960s, there were people in Russia, and also there was some work done in Germany in the 50s, and more recently in the 80s, there were also people looking at these materials in India. So this is a global level, but very sparse interest in trying to look at these materials. And so we knew we could make these materials, but the issue was how quickly can you make it and in what quality. So while we were working on these, there were a couple of other reports that came out where people took the equivalent oxide materials and tried to use an extremely aggressive sulfurization mechanism using CS2 to get powders of these materials. As you can see, these are fairly successful, but it's very defective material, and you can see the PL curve for some of these materials does not look as impressive as typical 3-5 wafers look like. So we decided to go about doing this, and we knew that just taking elemental sulfides and powders and mixing them and cooking them for a long time is not going to solve the problem. So we went about taking these powders. We also added a little bit of halogen. So the insight was to take halogen and make it and let it react with highly refractory, high melting point materials like zirconium, and that allows us to lower the melting point of this system, and hence the reactivity is a little bit better. So luckily, when we started doing this, and we found that within a day or two of cooking, our materials started to crystallize and they looked really homogeneous visibly. And we started characterizing them using diffraction, and we found that we were able to stabilize the barium zirconium sulfur 3 in the distorted 3D network connected corner shared perovskite phase. We also were able to stabilize the strontium zirconium sulfur 3 in the needle-like phase that I showed earlier. And also by heating up this material to high temperature and quenching, we were able to metastabilize the 3-dimensional corner shared perovskite too. So in some sense, we could even achieve 2 different phases of the same composition by just working with the way we are processing these materials. So our first generation materials were all powders, but nevertheless, structurally they were looking really good. We also did some chemical characterization of these materials using EDS and X-ray fluorescence studies, and we found that consistently in a semi-quantitative manner, they had the stoichiometric ABX3 composition, even globally and also locally. So the most important thing is to look at optical properties of these materials. So this is a busy slide, so I'm going to start with the right side. So these are theoretical predictions of the band gap values for or the density of states for the strontium zirconium sulfide alpha phase, strontium zirconium sulfide beta phase, which is the corner shared perovskite, and barium zirconium sulfide. And using the density of state values that we obtained, we were able to predict what was the absorption coefficient, and hence the band gap values for each of these 3 phases. And if you look at the diffuse reflectance spectra for the powders that we did, these values match closely with this. There is an offset because typical DFT calculations always underestimate band gap, but overall the trend was very similar to what we would expect. Not only that, when we did photoluminescence measurements, we were able to identify macrocrystalline particles in those samples that gave intense luminescence that allowed us to confirm that the diffuse reflectance studies showed the right band gap values. So the most surprising thing for us was that we made powder samples and we were able to get very intense PR, which is actually very surprising. If you have been working on optoelectronics of 3.5s, if you take a 3.5 wafer and crush it down and do PL, you'll see nothing, because the surface recombination will kill you basically. So in these cases, these materials somehow can survive that really well. So not only that, we took these systems and we tried to do quantitative luminescence to get a sense of how well they do in terms of the external quantum efficiency. And what we found was that if we use the same irradiation conditions, indium phosphide, cadmium selenide, single crystal wafers show PL curves that can be put on the same curve as our beta SGS. So this tells you that, I mean, of course, we are not saying that our material is better than any of the 3.5s, but in terms of quality, you can at least put them on the same curve, which is actually pretty impressive for the first generation material. So if we quantify how much, what is the luminescence efficiency of this system, we found that the luminescence efficiency was a fraction of a percent in external luminescence efficiency, and the internal luminescence efficiency was a few percent after we correct for absorption and reflection losses. So this is actually a pretty good starting point. You just have a powder material and it still luminesces really well. So my group is primarily interested in materials discovery. We are also starting to do a little more device work, but our focus was to try and figure out, can we tune the band gap of this system, which seems to have hit 1.5 eV, but right at the lip of the single junction solar optimum, can we push it a little bit further out? Okay, so that was the next question that we wanted to address. So there were a couple of approaches that we wanted to go towards. One is, of course, trying to lowering the band gap, where many people have tried to alloy these materials with titanium on zirconium side, but since they have very different crystal structures, they tend to phase separate, so it's not a very good solution. The other option is to look for a polar order in these materials, which was interesting to us because this whole predictions on bulk photovoltaic effect, where if you have a polar order in a semiconductor, even though your polarization need not be maintained very successfully, but if you shine light, this local polarization will help you split your excitons into electrons and holes in different directions, and hence it could help with charge separation much more efficiently. So this was something that we were a little bit interested. There was prediction that calcium 3 zirconium 2 sulfur 7, the Ruddlesden-Popper layered structure could show this effect. So we wanted to first start off with the barium zirconium sulfur series, which we have already started making these materials. So what we wanted to do is to take these materials, try to make these natural superlattices by inserting an AX layer in between the perovskite blocks and see how that affects the optical gap and their polar order. So to give a background, so this is the system that we were looking at, and if you take this barium sulfide, which is basically crystallizing in the rock salt form, and if you insert in between these two, you can form a whole series of superlattices, and these are called as the Ruddlesden-Poppers. So we started looking at the first one, which is barium 3 zirconium 2 sulfur 7, which is closest to the calcium 3 zirconium 2 sulfur 7, that could have some sort of a polar order. So when we did the DFT calculations, what we found was that this system was a little more symmetric than we wanted. So in principle, it's going to be hard to find polar order. But nevertheless, what we found was the optical absorption coefficient along the two-dimensional planes and across the two-dimensional planes were very, very different. And this, for some weird reasons, red shifted the band gap from 1.85 predicted value to 1.2 or 1.3 EV. So that means somehow you can take the three-dimensional perovskite, you make a layered structure. In principle, you should actually increase your gap, but now you have shifted it to the other side, which is kind of unusual for us. So we got excited about this trend, which solves at least one of the problems that we were interested in. So we wanted to go and dig deeper and try to make the whole series of materials and try to study them. So this is where we started growing crystals of these materials. Now the reason to grow crystals is that Ruddlesden-Poppers are extremely hard to stabilize in a powder form. Even if you did, it's very hard to analyze them because very subtle changes in the perovskite block thickness can immediately change the phase that you're looking at. So that's why we wanted to grow single crystals to make sure that it's reliably uniform in structure and composition. So we used a couple of methods. The one method that is going to be relevant for this part of the talk is the flux growth method. So you take flux, which is basically some sort of a low melting point material that you can mix this material with, and that allows you to dissolve the whole thing, and then when you cool it down, you recrystallize and you can grow crystals out of it. The other method that I'm going to show for the later half is the vapor transport method. We'll talk about that later, where we'll grow the next set of materials. So the first one, we were able to get the barium-3 zirconium-2 sulfur-7 in single crystal form, several hundred microns in lateral dimensions and also in thicknesses. And so we did chemical characterization analysis. We were able to show that they have the right composition. And when we did STEM measurements, scanning transmission electron microscopy, we were able to clearly see these two perovskite blocks sandwiched between the rock salt layer. So that also gave us confidence that we indeed made the right type of material. And when we did PL measurements, just like what was predicted, we did see a red shift off the peak from 1.8 EV all the way to 1.3 EV or so. So this was a very interesting point for us, and we wanted to take this further and try to look at this compound more. So we did the same quantitative luminescence measurement similar to what we did for the beta SZS, and we can again show that the quantum efficiency is external quantum efficiency is a fraction of a percent, and that even though we have gone to the single crystal form, in this particular material we haven't improved the surface quality enough to improve the quantum luminescence efficiency significantly. Nevertheless, it's interesting that this does show pretty good quantum efficiency. The other thing that we got interested in is to try and find out what is the recombination lifetime in the system. So this is another key metric that decides whether such a material can be a good solar cell or not. So if you have long recombination lifetime, that tells you that your material is less defective, and hence it can convert the photons into electrons and hole pairs efficiently. And what we found was when we fit this time resolved photoluminescence curves, we found that the lifetime was of as long as 65 nanoseconds, which is actually pretty good, even better than some of the SIGs and CZTS materials that people have been studying, which tells us that if we make devices out of this, there is a very good chance you can achieve very high quantum efficiency as long as you can make optimized device structures. So this is just a precursor that is present. It doesn't guarantee you that your device is going to be highly efficient, but this is a good sign that you have good materials to make solar cells. So continuing on this front, we got curious and wondered why this redshift happened. So to address this issue, we looked at the second compound in the same class, which is the barium-2 zirconium sulfur-4, and that also showed very similar anisotropy in the absorption coefficient in the two directions, and also showed very similar redshift that we saw earlier. So it seems very spooky now that more than one of these compounds theoretically are predicted to have redshifting despite having this layered structure. So to completely address this issue, we made single crystals of all the three different compounds that I showed earlier, and they were all characterized using the standard methods that I showed earlier, and we did photoluminescence studies on all of them. So now this summarizes all the value. So the barium zirconium sulfur 3, which you saw in powder form earlier, now shows exactly the same 1.8 EV even in the single crystal form, and 3 to 7 and 2 and 4, which is the n equals 1 and n equals 2 Ruddlesden-Poppers, they show close to 1.3 EV, slightly different in the two cases, but close to 1.3 EV luminescence emission. So that means your band gap is roughly there. It doesn't completely resolve the exact optical gap, but it gives you a ballpark number. Not only that, we are also able to see nice Raman peaks at room temperatures for all of these, which tells you that the material actually interacts nicely with light and is of really high quality. Okay, so let's try to put all of these things in perspective and see how does Ruddlesden-Popper band gap evolution work for various materials. Okay, so now I mentioned that strontium titanate is a very nice perovskite oxide. So this is the band gap evolution for strontium titanates, Ruddlesden-Poppers. We have picked a case of methylammonium iodide, which is the other perovskite that people like, and that also shows the same increase in band gap as a function of the layer thickness of your perovskite. But in our case, the barium zirconium sulfur based Ruddlesden-Poppers show exactly opposite trend. It basically shows a redshift. Okay, so now we have the whole summary. Theory agrees with experiments, but we just don't know why, and that's what we wanted to address. So we went a little deeper into understanding what's going on. Okay, so this is a very busy slide, so I'm going to take up a little bit of time to explain this part. Okay, so this curve that I show is the experimental value of various different phases of the perovskite, the n equals 1 and n equals 2 case for n equals 2 and n equals 1 case of Ruddlesden-Popper. You can clearly see this red shift that I shown earlier. Now, what happens is, in principle, most of the oxide and halide perovskite that we saw earlier did not have substantial difference in how this octahedral tilting that happens in these systems, but the dominant effect in all those cases was just quantum confinement. You just take a perovskite block, you put a layer, and hence you reduce the dimensionality of your system. So we took this material system and then we removed all this octahedral rotation that was present in the perovskite, and we got this PM3 bar M phase, which is a nice symmetric perovskite. And in that case, if we compare the trend with only quantum confinement, we do see an increase in the band gap. But if in reality, the system actually likes to distort a lot in the perovskite form, and as you make it lower dimensional, the distortions go away, and hence your band gap drops. And that is very clearly shown with the theoretical calculations also. So this tells you that in these materials, not only does the connectivity of these octahedra matters, even subtle distortion and rotation can affect your optical properties significantly. Okay, so that's something that we found as interesting, and perhaps that's a mechanism that one could use to tune the optical band gap, and hence how you can make different heterostructures of these materials. So let me summarize all the luminescence curves from various different compounds that I've shown here, and these are materials that span all the way from the green gap, which everybody is interested in for light emitting, down to the single junction optimal solar cell gap. So we have shown that these materials have luminescence in technologically relevant wavelengths for technologically relevant applications. The next step for us is to show that we can grow thin films of these materials, make some devices, and show that they do work very well. Okay, so that's the first half of the talk. I don't want to keep you guys for very long, but I'll try to go through the last bit fairly quickly. So the other thing that really got our interest was this corner of this prediction graph from Professor Shengbai Zhang's group at RPI, and there was this prediction that if you can crystallize hexagonal phases for this titanium-based compounds, you can get band gaps fairly close to the long wave infrared or mid-infrared range. Okay, so this is very interesting because, as I mentioned earlier in my talk, communication and sensing in infrared remains an important bottleneck, and that's something these materials could address. Okay, and as titanium is much smaller than zirconium, the chances that you would stabilize this hexagonal phase over the other phases is very high. So it's a good compound to study. So what are these hexagonal perovskites? So I'm giving the term hexagonal perovskite, which any true crystallographer will hate, but this is just to show that it has an octahedra that's connected and forms the hexagonal structure. So these are 1D chain compounds essentially, and they have these octahedra that are connected by the faces, and they form these rigid 1D chains. And if you take the AB face of this compound and you look at it, you will clearly see this hexagonal pattern that is very similar to most of the gallium nitride or graphene or of the honeycomb systems. So this system, when we wanted to study how does this light matter interaction happens in the system, is there any anisotropic effects that we could leverage? So we did the DFT calculations, and we were able to find the dispersion band gap band structure for this material, and the band structure itself looked very symmetric. So we thought that, okay, this material is probably, despite showing structurally very anisotropic features, may not be optically very anisotropic. But surprisingly, once we calculated the absorption coefficient, what we found was that along the 1D chains and across the 1D chains, the absorption coefficients are very, very different. And this is primarily because the coupling coefficients along the two different directions are very, very different. Not just the seemingly band structure being symmetric has a big impact. So this got us interested in growing crystals of these materials. So we picked this barium titanium sulfur 3, and we grew them in large single crystals using vapor transport method. It's exactly the same method. There's no flux though. In this case, you just have a halogen transport agent, and you can just grow large single crystals of several millimeters by several millimeter size. And you can see SEM images that these have very nice crystallographic facets and terminates nicely. And once we did scanning transmission electromagnetograph, we were able to see these 1D chain behavior that is very similar to what you saw in the schematics earlier, and also this hexagonal pattern that I showed. So structurally, these materials are really good. So then we got curious, and we wanted to know what is the crystallographic direction for the crystal plate that we have seen. Okay, so my students spent some time, and he started trying to figure out how this works. So when we did the out of plane diffraction on these crystal plates, we found that it has A-axis orientation. Okay, so if you have an 1D chain compound with A-axis normal axis, which means you have A-axis in the in-plane somewhere. Okay, now that means that if you take your system and if you rotate it by 60 degrees along this A-axis, you should be able to access the B-axis. Okay, so let me show this here. So this is your A-axis, and your B-axis is at 60 degrees away. So basically, by taking the crystal, aligning it along the A-axis, and then rotating it by 60 degrees, you should access the B-axis. So that's what we did here, where you first start with the A-axis, and then you rotate it by 60 degrees, and now you achieve the B-axis. So that tells you that you have your crystal like this, and your B-axis somewhere inside your system. That means the axis perpendicular to A-axis is your C-axis. So this allows us to completely figure out what are the crystallographic axes in your crystal itself, and that way you can tell what is the 1D chain axis in your system. Okay, so of course we also check for the chemical composition purity of the system, and with this information we started looking at FTIR spectroscopy to look at what are the anisotropies in the system. So this is the FTIR spectroscopy for your polarization aligned parallel and perpendicular to the C-axis, which means parallel and perpendicular to the chain axis. And just like the theoretical predictions, you could see that the absorption edge is very different along the two different directions. And consistent with the absorption edge from the transmission spectra, the reflectance spectra also shows the vanishing Fabry-Perot fringes at the right location where you hit the absorption edge. Okay, so these two things are very consistent, and using these fringes we can get an idea of what is the index and also the thickness of the material. We can't distinguish the two exactly, but we have a starting point to work with. So to get the exact optical indices for these materials, we started doing ellipsometry at the absorptive region, which is further here to the left of it. And ellipsometry gives you the real and imaginary part of the index, and using that information and combining this data, you should be able to get the whole optical indices for the system over a whole range. So this is a very busy graph on the left. So we are showing the absorption edge, the optical indices, the real part, which are shown in solid lines along the chain and across the chain, and also the imaginary part along the chain and across the chain. Okay, so this is essentially similar to the transmission graph I showed you earlier, and this is the interesting part now. So the real part of the refractive index for these two materials along and across the chain are completely different, which tells you that you have produced a highly birefringent material, which is which has some interesting applications for linear optics and so on and so forth. So we took this optical indices and we quantified the birefringence and also the dichroism, which is how different the absorption characteristics are between the two different directions. And what we found was that the dichroism showed a very broadband large value, and also it's turned over at some point. But the birefringence, which is this real part of the index, is very, very large compared to most materials that we have seen. So how high was it compared to most materials? So we picked most of the birefringent materials that are reported in the literature and are well known, commercially used, and we compared it with our material, and we found that over the whole energy range of interest, this was at least 3 times larger than the next highest birefringent material that we knew. Not only that, this has almost 10 times larger birefringence in the mid-wave and long-wave IR region, where almost no birefringent material currently exists of any appreciable value. Okay, so this is very interesting for us, because now you have created a scenario to take light, and your light matter interaction is going to be extremely different in the two directions. And now this forms a basis for you to build very specific polarization resolve sensors and so on and so forth in this direction, where there is very little optics and also detectors that work very well in this range. Okay, so why did this happen? So for many years people have been synthesizing materials, should not be so complicated, right? So it turns out taking the polarizability of individual elements and trying to distribute them along two different directions is not an easy challenge. And we were lucky enough to come across this type of structure that we got interested in, where it forms an 1D chain compound, and also we picked the right type of elements. For example, sulfur has very high polarizability compared to oxygen, and that's what allowed us to get very large index difference along the two different directions. So this one is not a one-shot thing. So we were able to grow single crystals of the strontium titanium sulfur 3 compound. It forms a non-stoichiometric, slightly off-stoichiometric material, but nevertheless shows very similar trends in transmission reflection spectroscopy in the IR, and also has high birefringence. We haven't been able to measure the real part of the index because of the size limitation in the absorptive regime, but nevertheless it shows very high dichroism compared to most other materials. So overall, with these stories, what I'm trying to impress upon you guys is that discovering new materials, trying to make them in sufficiently good quality to really understand how the physical properties evolve, is actually a very important step that allows us to make materials for next generation devices and technology. Okay, so I hope I hope I have convinced you guys that perovskite chalcogenides with transition metals are interesting photonic materials that have tunable band gap in the visible infrared region. Not only that, it has very interesting properties for making solar cells, detectors, and more importantly, emerging infrared devices and optics, which is something that is very lacking these days. So that's the end of the talk, and I would like to acknowledge the students, specifically Shanwan Niu. He did all the synthesis work, and also he coordinated a lot of the projects with our collaborators. We had several wonderful collaborators all over the world. Han Wang at USC, Rehan Kapadia, Mikhail Katz at Wisconsin, theory collaborators David Singh, Anderson Janetti. We also had some nice work with AFRL trying to look at the microscopy of these materials. And without their contributions, I don't think I would be able to present any of these things. We also were fortunate to get some federal support to do this work. So that's what allowed us to explore these materials without worrying too much about funding issues. So that's the end of my talk. Thank you. If you have any questions, I'll be happy to answer.
So for that last set of the high birefringence optical anisotropy materials, so if you wanted to use those for kind of applications, would you have to grow large single crystals, and how would you go about doing that?
Yeah, so that's a very important question. So So growing large single crystals in sulfides, for example, if you look at the graph that I showed, there's a lot of effort in growing these chalcopyrite type, nictide and other sulfide type materials. And most of the times people are using Bridgman type method to grow it. You can also use traveling heater methods. There are different ways where you can make it larger. Right now we are using vapor transport. It's not a scalable technique. You can get a few millimeter size crystals if you're lucky. But Bridgman is the way to go to make larger crystals.
So one of the things that you showed was that the recombination time
Mm-hmm.
was pretty large, right?
Yeah.
So what is preventing you from making a solar cell?
Yeah, good question. So, so right now what we are trying to do is to, so as you can see, the crystals are 100 microns by 100 micron size, which limits our ability to freely do lithography on those systems, because it's a very awkward size where you can't put too many contact pads to make devices out of it. But nevertheless, we have started trying to polish them, try to embed them in a resin and try to put contacts on top. So we are trying to do transport measurements first to get a sense of what are ohmic contacts for this material. And surprisingly, I mean, it should be clear because of the recombination lifetime, all these materials have very large Schottky barrier, which means that they are fairly close to intrinsic as it gets. So doping them gently will also help to figure out ohmic contacts on one side. So there are multiple things that we are trying to address at the same time, so that you can really make a solar cell out of it. There are developments in carrier selective contacts which will allow us to make solar cells, but nevertheless you need to address the dimensionality of your structure. So that's what is limiting us right now.
Any other questions? All right, let's thank our speaker one more time.